Hi, ladies and gentlemen. Our next unit from modern physics is nuclear physics, which is about the nucleus of the atom itself. So before we actually talk more about nuclear physics, let's do a little bit of review. The components of the atom are the proton, neutron, and electron. But it's important to keep in mind what exactly is holding the atom together. With the electron and the proton, it's kind of obvious because the fact is we have a negative charge here, we have a positive charge here. They're going to be attracting towards each other with an electromagnetic force. Okay? But when you start talking about the inner workings of the nucleus itself, well, inside the nucleus, we have neutrons and protons. And the problem is that those protons are positively charged and they want to repel away from each other, but they can't. And that's where we start talking about the fact that there's some sort of binding energy that's holding the nucleus together. And we call this the strong force. Okay? Or sometimes also called the nuclear force. And this force is holding the protons and neutrons together. Otherwise, they would break apart. Another thing to review, atomic number and atomic mass, or mass number as well. When we deal with, let's say, helium, as in our first example, the atomic number is 2. And the atomic number deals with the number of protons. When we're talking about the mass number, that would be that number over there. The mass number is equal to the number of protons plus neutrons. And so therefore, in this example over here, helium would therefore have 2 protons and 2 neutrons. And any sort of isotope of helium would have a different number of neutrons, but you cannot have a different number of protons in an isotope. So let's just write that down. An isotope has different number of neutrons. Now, before I go any further, I should also quickly review what's the difference between atomic mass and mass number. When we're talking about atomic mass versus mass number, I've already defined mass number to be the number of protons plus neutrons. The atomic mass is actually an average mass of all the existing isotopes. And yes, the number often appears to be very close to a mass number, but it's never exactly the same. That's because we're actually measuring the atomic mass, and the unit that we use, or that you guys are using in chemistry, were atomic mass units. So AMU is what you use in chemistry, but we're going to use U to represent our mass. So when I look at the number here, 232.037 U, that would be the mass of, I believe, uranium. It's also good to keep in mind the conversion factor. One atomic mass unit is actually equal to 1.66 times 10 to negative 27 kilograms. So it's a very, very, very tiny number. And if I wanted to convert 232.037 U into kilograms, I would simply just have to use my conversion factor. So 232.037 U over 1. I'm just putting my example up here. 1 U is 1.66 times 10 to negative 27 kilograms. And I would end up with 3.85 times 10 to negative 25th kilograms. Now, in the next part of our unit, we're actually going to start talking about Einstein's famous equation as well, which is E equals to mc squared. About the equivalence of mass and energy, how really mass is really just made out of energy, and energy is made out of mass, and vice versa. And one of the conversion factors that we're going to end up dealing with later on also is that one atomic mass unit can be turned into 931 mega EV. And we'll get to this more later on, but just keep that in mind as another possible conversion factor. So if I want to convert 4.003 atomic mass units into energy, 1 U is 931 mega EV. This would equal to 3,726.793 mega EV. Mega, of course, means times 10 to the 6 EV. So one little bit of mass can generate a lot of energy. Okay. So before we talk about Einstein's famous equation of E equals mc squared, let's talk first about something called the mass defect. Now, scientists noted that if they actually found the mass of a helium nucleus, in other words, they have 2 protons plus 2 neutrons, and they found the mass. But if they took those 2 protons and those 2 neutrons separately and weighed them as well, or found the mass of them, for some reason you would think that they would balance. But they didn't. In fact, what usually happened was that the mass of the separate components was greater than the mass of the helium nucleus itself. Somehow, some of that mass had disappeared. If we look at our chart, we have the rest mass of a proton and neutron. And we know that the helium nucleus has a total mass of 4.0026. So individually, if I take these particles, 2 times 1.0073 U plus 1.0087 U times 2 also, and I added up all those masses, I would see that the total mass for those separate components would equal to 4.032 U, which is greater than the 4.0026 U. That missing mass is what they call the mass defect. So if I subtract the 2 numbers over here, my mass defect ends up equaling to 0.0294 U. Where did that mass go? Well, the thing is, when they took the 2 protons and 2 neutrons and they came all together, some of the mass actually turned into pure energy. In fact, it turned into the binding energy that holds the entire nucleus together. Or the strong force. In fact, if I wanted to figure out how much energy that is, I could then, well, convert that. So it would be 0.0294 U over 1. 1 U equals to 931 mega EV, which is equal to 27.37 mega eV. Okay, so that's how much energy was created by the mass to hold the nucleus of the helium together. So now we bring it over onto the whiteboard over here. The same work as before. We calculated how much mass defect there was, and we calculated how much energy that turned into. And I want you guys to understand that when I did 1U equals to 931 mega eV, that was actually the same thing as doing Einstein's E equals to mc squared formula. Except the only difference is that E equals mc squared deals with joules instead of electron volts. So if I actually wanted to solve this, how much energy was turned into the binding energy using E equals mc squared, I would first take my 0.0294 and convert it into kilograms. Which would equal to 4.88 times 10 to the negative 29 kilograms. And if I use the formula E equals mc squared, I can see that the energy that was created is 4.88 times 10 to negative 29 kilograms times the speed of light squared, which is equal to 4.39 times 10 to negative 12 joules. Okay, so that's how much binding energy was created when the protons and neutrons gave up some of its mass and became a glue that held together.